Hi guys, this is Math 148, section 10.4, and in this section you're doing more applications with maximizing and minimizing different situations. So the three problems that seem to come up in this section are problems that involve fences, so you're minimizing the cost of building some sort of enclosing a space with a fence or something. Another one is volume. This is where you're trying to find the maximum volume for a box or whatever. And then inventory, where you're minimizing the cost, trying to figure out how many items you should do per production run. So I'm going to go over a problem for each one of these, and it may take a lot of videos because these problems are a little bit long. But the first one I'm going to look at is a fencing problem, and not fencing like the martial art with swords. That's also cool. So this is what the problem is. It's question number 17 on page 681, and they have a fence. And this problem is really similar to example 5, which is the property development problem. So the question reads, a rectangular field with one side along a river needs to be fenced. Suppose that no fence is needed along the river. The fence opposite the river costs $20 a foot. And the fence on the other side costs $5 a foot. If the field must contain, or enclose, 45,000 square feet, what dimensions will minimize the cost? And you can pause this if you don't have the 10th edition, you can reread this question. So when I read this question, I have a lot of things that come to mind. So I wonder, why is the one side of the fence so much more expensive to build? What are you doing on that one side? Are you building, piers and columns? Is it a cement wall? What's going on that one side? And why do you need to enclose those specific dimensions? I'm kind of curious about that. I can't picture this scenario very well, you guys. And then why do you not need a fence along the river? What are you trying to fence in or out, right? You're trying to keep wild buffalo from coming into your cornfield, and why won't they cross the river? So I'm never going to have answers to these questions, but if you read this problem and you were thinking this too, I think they're very reasonable questions. But for our math situation, we just have to go ahead and work the math. I just bring those up because were I ever involved in a consulting situation like that, those would be my first questions, like what's going on with the river. So here's the river. You like that fancy river? And here's our fence. We're going to do these two sides of the fence, our green lines, and then this side of the fence here, this is supposed to be a perfectly square fence. And that's another question, is your fence perfectly square? Oh well. So on this side, we're going to let this side of the river be X. This side is X, and it's the same. It's a rectangular fence, and both of these are $5 per foot to build. And on this side, we'll call this side that is parallel to the river Y, and that is $20 a square foot to build it. So I'm letting X be the length of the fence. So X is the number of feet. So X is not equal to 5. X is the number of feet. And similarly with Y. So now we have to put all of these equations and sentences into two equations where we can solve and minimize the cost. And here's how you do it. The first thing you know, I guess I'll put this in yellow, is that the area that you are trying to enclose, and according to our formula, this equals X times Y. That all of that is going to be equal to 45,000. Comma. We also know that the total cost, we want to minimize the cost. So let's make a cost function. Cost function, I'm going to write in terms of X, but this is going to be the total cost of building our fence. This is going to be equal to $5 times X, right? That's the cost for this side, plus $20 times Y. That's the cost for building that side, plus $5 times X. I just added up the three sides, 1, 2, 3. Most of you will just put this right together and say that is 10x plus 20y, because the cost to build this side is going to be $5 a foot times x number of feet. So that's how you get that. So we can't minimize this function until it is in one variable. See how there's an x and a y? We have to make it all in terms of one variable. Personally, I like to have it all in terms of x, but it doesn't really matter. And you can reverse these. You can have that be y and this be x. It makes no difference whatsoever. You'll get the same answer. So in this case, if we look at this area equation, this is sort of a math 116 kind of problem where you take one function and you write it in terms of the other variable so you can plug it in and substitute. So now my cost function, so I use the area function to find out that y equals 45,000 divided by x. So now my cost function is equal to 10x plus 20, and now instead of y, I'm going to use this thing, 45,000 divided by x. Ta-da! We're not done yet. Oh no, that would be far too simple. So now we have to minimize this cost function. We have to minimize it. And minimizing it means we're going to take the first derivative and set it equal to 0 and find out which x values make the first derivative equal to 0. So in this case, the first derivative is equal to 10. All right, that's this piece. So I'm just going to make a little note here. This part here, 20 times 45,000 divided by x, that's the same thing as 90,000 times x to the negative 1. Do you see that? X to the negative 1. Okay, so now I can just write minus, so I'm taking the derivative of this piece. You take the negative 1, multiply it by 90,000, you get negative 90,000 times x, the derivative of this one, subtract 1 to the negative 2. So now we're saying, when does this equal 0? You'll find out on the next page. This is the cost function. The derivative of the cost function is equal to, I'll postpone that, 10 minus 90,000 divided by x squared. When does this equal 0? This equals 0 when x squared is equal to 90,000 divided by 10, which is equal to 900. So this all equals 0 when x is equal to plus or minus 300. Now, because we are dealing with areas, we have to have x be greater than 0. You can't say, good news, Mr. Farmer, your fence needs to be negative 300 feet long. It needs to go in the other guy's property, right? You can't do that. So we're going to ignore the negative 301 and just look at the x equals 300 solution. So I'll go back to yellow. So we suspect that the answer is x equals 300. But before you can run away with this and say, ta-da, x equals 300, I'm done, I'm out of here, you have to check to make sure that this is, do you want it to be a maximum or a minimum? Well, go back to the problem, in case you don't remember. We're trying to minimize the cost. So we want to make sure that x equals 300 is a minimum. And you can do this with your first derivative test, which is from section 10.1. You have 300 over here. And which values did I pick to check? I picked 200 and 400. All right. So you check by saying, what is the first derivative evaluated at 200? So you take 200 and you plug 200 into here. 10 minus 90,000 divided by 200 squared gives you negative 12.5. You can try that. The point is, it's negative. So you think, okay, this side, the function is negative, like that. And over here, the first derivative at 400. So again, we're plugging 400 into the first derivative, not into the cost function. That's going to be equal to 4.375. That's a positive number. I actually did the math there, and I'm sort of shortcutting a little bit. So you're plugging 400 into this number. So this tells us that the function goes down and then up. So at this point here, because it changes sign and it goes from negative to positive, that means 300 is in fact a minimum. So we're done. No, we're not done. I was kidding. Oh, that's a hilarious joke. So here's our river. So the actual question says, what dimensions will minimize the cost? And it doesn't ask for the minimum cost, so we can just go for the dimensions. So we said x is 300, so our dimensions are 300, 300. So the question is, what is this little y? I won't make it blue. Blue stands for water. That piece there, remember it was 45, we said y equals 45,000 divided by x, which we now are saying is 300. So y is going to be equal to 150. 150. So these are the dimensions that minimize the cost. 300 feet, not 300 miles, 300 feet on either side that runs perpendicular to the river and 150 feet on the one side that runs parallel to the river. So there is your answer. Ta-da! Okay, I'll do another problem from this section on a different video.